So I'm a researcher at University of Bergen. The work I'm presenting now has been done in collaboration with some colleagues in Bergen, which are listed in the second line, and also people from other universities. So I divided my presentation in three sections. Basically, I will present how we do model the coupling between the solid Earth and the surface processes in our models. We'll show some feedback mechanisms that we have identified, especially in extensional settings. So during the last several years, been focusing on extensional system, so from continental rifting to seafloor spreading, basically. So I will focus on this today. And then in the last section, I will show two kind of case studies, one based on 3D models and the other one based on 2D models, and then try to write some conclusion and discuss some of the challenges or of the effort of coupling surface processes on thermomechanical models. So Earth topography, which is the key object here, it's interface between what's the outer layers of the Earth, which is composed of the hydrospheres, the biospheres, and obviously it's where we live, and it's where the life have also been evolved through time in the geological story. So that's important to know what controls this topography evolution. So nowadays what we know that the Earth surface elevation depends to first order on crystal and lithospheric isostasy, which is the compensation of the crystal and lithospheric load on the viscous upper mantle. It also depends on strain localization. So basically, we know that on Earth, the plates tectonics moving, they deform at their boundaries. And we do have some seismicities that show illustrates the effect of this strain localization along fault plane, which are seismic behaviors. And it's mostly localized on plate boundary, where we do form a lot of topography, both along rift system, like for example, if I can use, so for example, along the East African rift system, or along basin and range. So in the last component that might control also the topography is the deep density anomalies that are embedded in the convective mantle. But so far, outside this active domain and also outside of the anomalous case, the average elevation of the continent is about 400 meters. And then we have some anomalous topography, for example, South Africa, east of South America, Western US have some anomalous elevation. So then we have different landscapes that we can classify. Basically here from left to right, it's just a selection of random different landscapes. One in Western US, Colorado, some in, again, basin and range or the East African rift system. Also offshore, along the mid-ocean ridge, we do have some landslides. And then we have a lot of topography also in the mountain range, which, for example, in the Alps or in Taiwan with some landslides. And they all depend on the tectonic activity, or we could say vertical motion, but also on the surface processes efficiency, which depend on erosion, sediment transport, and sedimentation. On most of these processes on Earth, most of the landscapes we nowadays have can be, depends to first order to fluvial incision. As we can see, for example, along a reef flank on the left here, or also in the more passive domain, in the Aero, in the bottom left. Also in active domain, also in Taiwan, where you have landslides on rocks going in the valley shape of the insides valley. So both this fluvial incision and this gravity-driven mass movement last landslide, which we'll describe as e-slope processes, on sediment transport are two first under controlling these surface processes. On climate, which is precipitation and temperature, base level, which control the sink of the sediment which are transported by the rivers. The lives, which control also the stability and of the soil. On the rock properties, basically mostly the cohesion that control to first order this erodibility on these surface processes. So in my work, I mean, what we want is to model the long-term coupling between these two internal processes and surface processes. And to do this, we have developed a coupled thermomechanical surface process model to understand this interaction, both in 2D on the right, on the left side. We can see a continental rifting phase followed by continental breakup, lithospheric breakup. So you can see on top the crust will systematically use the same color in the next slides. So basically the crust, continental crust will be orange and white. And then the lithospheric mantle is greenish colors. And then the yellowish color will be the sublithospheric mantle. But we also do it in 3D, and there are these two different aspects that we'll develop in this presentation. But the idea in this approach to assess the relative importance of tectonics on surface processes, on structures, on elevation of passive margin, but also on mountain belts, and to better understand the fluvial drainage network evolution on source to sink problems that mostly can be done in 3D. And the final purpose of this modeling is to interpret the stratigraphic data, the base level evolution, the climatic signal, and also a more pragmatic reason of doing this work is for exploration for oils or gas. So the surface process, for the surface processes model, we use the stream power law equation, which is quite a typical approach, as I said before, as rivers are the first order mechanism. So the river erosions, they are modeled by the stream power law, which is here in red, which is a function of, it's basically the derivation of the shear stress incision that might happen in the riverbed. And it's function of the erodibility, Kf, the drainage area, the upstream drainage area, which is A, and then the slope of the rivers, which is defined by S here. And then we have two stream power exponent, M and N, which are basically determined by comparing on statistically the river profiles. On basically M is around 0.5, 0.4, on N is close to 1. And it's called extended because now we also take into consideration the transition from detachment limited, which is mean erosive limited erosion of the riverbed, to transport limited. So we have this factor, which is in green here on the right, which is called the river deposition parameter, which depends on the upstream erosion efficiency. So this is for the fluvial erosion. And for the hill slope processes, we use a diffusion equation, which is here in black in the center. And it depends on the diffusion coefficient, Kc, on of course of the gradient of topography. And then we have uplift. So the variation of elevation first depend on uplift, and the uplift is in our models provided by the thermomechanical model. So this is for the onshore part. In the offshore, we solve, in this case, I'm describing the case of the fast cap variation here, where we used diffusion as well equation for the offshore. And we have two different coefficients of diffusion for the silt and sands, so depending of the grain size. To describe the variation of the sediment elevation change offshore related to the sediment flux. So the 2D, these equations, they are solved using a Eulerian finite difference scheme in FastCap. We'll come back to this later. And we use the advantage of this approach that in this case, we use an implicit scheme in time to solve the stream power that make it really efficient and rapid, and also stable with a long time scale or time step. And we use a ON algorithm, which means that to solve for this equation, it requires a definition of a base level. But this makes the solution efficient and really adapted to the modeling approach. So we use a quite typical approach now. We use a finite element modeling of the stock equation for incompressible fluids flow. Is it coupled to the heat equation using the Boussinesq approximation? So each of these layers are defined by density. On this density is dependent on the temperature. It also coupled to temperature through the rheologies. So we use a viscoplastic description, which is more Coulomb for the plastic parts, on the dislocation creep, which is thermally activated power law, which means it's also coupled to the temperature. Now for the fall strength and the strain localization in this model, we do have what we call strain weakening parameters. Basically, we reduce the cohesion on the friction angle with strain, which represents the weakening of the fall strength related to the row pressure, phase changes on friction weakening along this system, along the shear zones. And this is for the 2D model, and we have in this model the advantage of this modeling, which in this case we use a code which is called Phantom. We solve it in an arbitrary Eulerian Lagrangian approach, which is a particle in cell approach, basically. It means that we have a free surface on top, and this is really practical when we need to couple surface processes on mechanics is relatively easy to implement. On both sides, we have free slip boundary condition, where we impose the lithospheric extension on the lithosphere, and we have an inflow in the mantle to balance the loss of mass during extension. So then we couple these models. So we couple it we have a 2D version where we couple the 2D model with FastCap, which is shown here with a kind of T models. And basically, what we do is we actually propagate in a cylindrical way the uplift function to the landscape, and then when we come back to the models and we do an averaging that we send back to the thermomechanical model to update the free surface elevation. And also in 2D, the advantage of the 2D model is we can use FastCap on top, but we can also use more simple 1D alternative models for surface processes. We'll come back to some examples later. In 3D, we have Farscape on top, and it's exactly the same description. So it's a viscoplastic as well. We have free slip boundary condition on the two sides, the north and southern sides of the model boundaries. On the in that case, the way, I mean, it's a really costly code, which is highly parallel, that we run on HPC servers. On the design and of this code is dedicated for HPC. So the 2D models, they are computationally cheap and offer rapid implementation of new simple processes model. They also allow for calibration or optimization approach to constrain the parameter space. But to explore the effect of 3D fault propagation on linkage or inheritance and obliquity, we have to go for the 3D thermodynamical model. So we'll go through different feedbacks that now can be modeled with this couple model. I will first do this simple overview, what controls the normal faults offsets during extension. So here on this cartoon, you have a brittle layer, which is drawn on you have a brittle layer, and then beneath it, you have a ductile layer, which deforms viscously. And then you have this normal fault. On the force you need actually to slip along this discrete fault depends on 4 parameters, which is the frictional resistance along the chasm, and also the viscous resistance, which is less maybe important in the viscous domain. The bending, so the resistance to bend of the brittle layer, the resistance, also the force you need to actually support topography that you create during the bending of the footwall. And then you have the flow. So the ability to the ductile part to flow and to allow for the fault to actually slip. And we know that if you remove by erosion the topography that you form, this one work done by Jean-Arthur Olive in 2014 and 2022. And basically, depending of the thickness of this brittle layer on the erosion rate, you might facilitate and preserve the activity of the normal faults, and you therefore will increase the normal fault offsets. So the erosion reduces the work to create new topography and then allowing accumulation of more offsets. It's basically what we would expect, for example, in the Western United States, in basin and range, where the whole reef system is actually, as I said in the first slide, in an anomalous case where it's actually subaerial condition. On all these faults, some of them have quite a high erosion rate, and that might explain a longer offset which is observed on this system. And also the second thing which is important is that if the force you need to slip on this fault becomes too important compared to the creation of a new fault, which could be in the footwall or in the hanging wall, then this can trigger, so the fact that we have erosion on deposition might trigger a different pattern of strain migration depending on the brittle thickness. So this is what we know, but what we also know is that in a reef system, from the initial phase of distributed crystal deformation, which we see in the first on top of these figures, to the breaking, to the lithospheric breakup, we know that the strain migration, lithospheric and thermal necking cause efficient strain migration towards the necking axis. So it means in that case, for example, if you consider that the sea level is 300 meters below the initial model top, it means that the effect of erosion will be only limited to the phase of distributed deformation, the first phase, or in case of anomalously elevated reef system like basin and trend or East African reef system. But after that, during necking, and after necking, during the distal margin formation phase, everything is offshore, below base level. So in that situation, if we consider this normal situation, if we apply erosion, in that case, we use a similar formulation, except that it's a 1D solution in these models. We have a case with now without surface processes on top, with surface processes in the bottom. What we see is that we have a significant change in the risk structure compared to the model without surface processes. We keep having this high angle normal fault, but what we see first is that we have much more strain localization, so the margins are much narrow, and they accumulate much more offsets. We can also see the effect of erosion. I don't know if you can see the you have a grid which shows the degree of bending on erosion on the left part, on the left margin, that shows that we have increased, facilitate the bending on the, but also the subsidence of the hanging wall has also increased the final offsets. And then we have also different feedback. The host formation and the outward migration are inhibited by erosion and sedimentation. We also see slightly on the right margin that the synthetic faulting is enhanced in the proximal domain. And now if the crust is a bit weaker, we have similarly, we see that we have a synthetic faulting and we see the erosion on top of the footwall. But we also see that we have this synthetic faulting in the proximal domain. What we can remark in that case that sediments cannot reach the distal margins. However, we know that in many systems where the margin is really wide, we have sedimentation. So the only way in these models, in these specific models, to reach the distal margin on half sedimentation is to lower the base level. So with a low base level, the sediment can bypass to the distal part and therefore can create some interaction between deposition and deformation. And in that case, we have interactions that between the tectonics and deposition, which is controlled by the lower crystal flow, which allow for this large tilted sedimentary succession on the formation of sag basins that we can see on the right. So now if we go in the onshore part, so this is the topography that we see in time for one of these models. We can see the topography onshore, which is in brown here, and then the offshore part is in blue. And you can see the shape of the reef flank just after during the Saint Rift. And it's in these models, it's quickly eroded, but it's not so much the amplitude which is important here, but more the variation that are important. So it's quickly eroded, and then we have a fast phase of retreat. On this happening because when the drainage network, which is oceanward first and just limited by the water divide, which is the highest topography along the reef flank, on the coastline, which is the shoreline. If suddenly the drainage captures the internal fluvial drainage network, it will suddenly get access to a really high, wide drainage area. And this will suddenly increase the sediment flux, and therefore the erosion rate, and therefore increase the retreat of the reef flank. But suddenly, what you can see here is that you have a decrease of this retreat. And this is a consequence of the regional isostatic response to erosion. So a fast erosion compared to uplift will trigger this capture of the internal drainage network. But as soon as this triggers the isostatic response, then they will stabilize the water divide and reduce the speed of the drainage divide migration. So now we'll go through a few cases. Two cases, one in the equatorial, based on 3D models. So we model the oblique continental rifting and design a setup which is inspired from the equatorial system, which is, I would say, one of the most prominent example of segmented system. So what you can see on the right here, you can see the margin which is segmented by long transform system. On this transform margin, they have like almost 600 kilometers long along the margin, and they are separated by rifted segment. So what we have done is we have defined a model setup with an oblique inheritance damage zone, which you can see on the top left here. You have a damage zone which is in now green, greenish colors, and then you have some seeds which are fully weak. And it means, so what it means is damage zone it's a zone where you have a initial plastic strain. So in that case, we have 30% of strain. It means that if you look at the bottom right panel about the strain weakening parameter, it means that you are closer to the threshold for weakening. It means that it's weaker than the surrounding material. And in this band of damage zone, we have defined seeds, two seeds on the boundaries, which you can see as propagators, if you wish, of the deformation. And then you have elongating seeds, which represent some inherited heterogeneity or weaknesses that we see as illustrated on the right by the geological observation. On the model in that case is 250 kilometer deep and is really big. So the idea is to reproduce or have a large scale model that can provide or enables regional landscape modeling. It has also the advantage that it mitigates the influence of the free slip boundary conditions that we have here on the north and on the south. So in that model, we apply lithosphere extension on both sides, on the east and west side of the model box. And then we have inflow to balance the mass lost from the bottom of the model. Otherwise, it's the same as before. We have extensions that we apply on this model, 1 centimeter a year, and we have a 125 thick lithosphere and 35 thick continental crust. If you remember, maybe I was not, but the parameters that we use for the strain weakening has to be carefully designed, that they can reproduce the characteristic fault offsets that we've been using in the models before. So here it's an example. So we have extension, and we have relatively low erosion efficiency. So we apply extension. So the two blocks move apart and then create this necking zone that lead to lithospheric breakup. And then if you look at the morphology, you form this reflanks topography through time. We see the formation of this large catchment almost systematically at the same position. And we have some topographies that are preserved and quite important. As you can see here in the outer corners, we have this long-term survivals of quite large topography. Along the reef flank, in that case, some of them, they are lasting and quite narrow. On some others, like the one on the right plate, show some capture on initiation of capture of the drainage network. So now if we do some comparison, useful comparison, we compare the same model, which was now it's called model M2, to the model without surface processes. And we can learn many things comparing these two models. First, we see that the surface processes, they do change the geomorphological evolution by, I would say, 3 observations. First, you can see that the strain is a little bit distributed in the damage zone on top in the model without surface processes. So you can see some irregularities on the free surface. But because we have lake deposition in the algorithm, we do have some smoothing, and you don't see any more these structures in the landscape on the model in the bottom. Also, the reef flank elevation is much more limited through erosional processes, which is quite obvious. And also, you increase the elevation of the outer corners, as I mentioned before. And this is the flexural response to erosion. And you can compare here, you can see on top, along the transform margin, you have almost no topography or irregular topography, but not really high topography in the outer corners. But as soon as you apply erosion on the system, then you create a lot of flexural uplift along the transform system that creates some topography that even sometimes more significant than the reef flanks themselves. And if we increase the erodibility, we trigger this big catchment evolution, and mostly all of them, as you can see in the bottom, they all think in the inner corners. So always in the continuity of the extensional system. So, and this is something that we observed also in the equatorial system. So most of the largest rivers, they all connect to the inner corners, which is a subtle feedback between tectonic and erosion. And it's a direct response to the tectonic, which the slight propagation, which is really small in that case, almost invisible, is sufficient to trigger the early Saint-Rift evolution of this river catchment and capture of the internal drainage network in this system. And what we see, even if we increase the erosion rate, we still preserve this outer corners high in the high erodibility case. And to finish a description of this and to compare to the 2D model I showed before, you see that the drainage, the water divide, which is defined initially by the reef flank, is actually, in that case, preserved, well preserved, and the isostatic response to erosion, to efficient erosion, preserves the divide, and then define this wider oceanward catchment along the rift segment. This is the last case before I go to some conclusion. So it's modeling that have been done recently about modeling the late Saint-Rift evaporate deposition along wide rifted margins. In that system, you have a giant salt basin, and it has the following key characteristic. So it's a magma pore system. So here on the profiles, profile 1 on profile 3, you can see it's wide margin. You have almost no magmatism along this margin. The oceanic crust, which is here in gray in the distal part, has a normal thickness. It goes from 5, 6 to maybe 7, 7.5 in the southwest parts along the Espírito Santo or Campos Basin on the Brazilian side. Otherwise is normal thickness. So it means that there is no massive or important temperature anomaly in this system. What also is important, the Saint-Rift deposit, which are in yellow along the cross section, they are all continental lake deposits. So there is no marine deposit in this system. And finally, we have some salts, which is here in pink, which are basically a different range of evaporites deposits in this system. And they do form some overlap on some distal eye. And we can also see some erosive inconformities, which is more for the interpretation of the final result, which is important. But the main observation is that in the north, in Gabon, which is the line 1, you have a lot of Saint-Rive sediment. You can see the really thick yellow layers on top of the continental crust. And if you compare with the Cuenza line, which is line 3, you have a really thin layer. So here you have two curves that show this variation from north to south. So on the left, you have the salt thickness, and you see that it's on average about 600 meters in the distal margin thick in the north, in Gabon, on almost 2 kilometers thick on average in the distal margin in the south, in Cuenza. And you have the opposite trend. So you have this anti-correlation between Saint-Rive thickness on salt thickness. This is the key observation, but this is a highly problematic system because is known that, or at least believed that the salt evaporate deposition might happen at shallow depth. So it would mean in the first case that if it's close to sea level, because you need some salty water on brines, if you are close to sea level, that it would mean that you have two situations. The first one will be to consider that you have a low topographic gradient between the proximal and the distal, and then it needs to be explained. Or it could be explained by a higher topographic gradient, but then it will need kind of a local deep sea level and aggradation from the distal to the proximal part. So the question now, we have a couple model, is trying to solve this question: what is the absolute elevation of the distal margin? What is the water depth of the distal margin during the late Saint-Rive? Can we explain this without considering any anomaly? So that's we're gonna try to do. So the model that we use, it's the same model as before. On the difference here is that now it includes the mel prediction, and it also includes the calibration of the density structure. And this allows to actually reproduce the mid-ocean ridge elevation. So it means that the isostatic response of the system is calibrated. And the reason why this is possible is just because we use the same boundary condition. It allows a stable model elevation, and it also allows to define an absolute base level, which is used for to define the accommodation for sediment deposition, but also to define the water load. If, for example, in this model, I remove the water load, which is maybe the case, as I said before, then you obtain exactly the same structures or similar, but the elevation is now, the difference in elevation is now 2,200 meters compared to the previous case, which was 3,300 meters, which is basically what we observe nowadays on the mid-ocean ridge elevation. And it also allows to have this calibration of the density structures. It allows for the lithospheric mantle, the continental lithospheric mantle, the greenish color on top, you can see beneath the crust, to actually flow, counterflow during the rifting, and allows for the magma pore system, allows the margin to be magma pore. So then we have run this model, and we now provide a model which is coupled with, in that case, marine aggradation. That's the only surface process model that we have on top of this model. And we calibrated it to actually reproduce a key characteristic, which is the distal margin width, the average crystal thickness, the distal margin average sediment thickness, including compaction of the sediment layer, on including the fact that we have no melting. So it means, this is the main assumption, it means that if we do reproduce these characteristics and we do reproduce the accommodation for deposition, and we use this assumption that in the 2n member case, so on the left, you have a low sedimentation rate. On the right, you have a high sedimentation rate. And you can see the topography of the distal margin here. In the bottom panels, you see that this value, sediment thickness and crystal thickness, they do fit the observation for Gabon on the right and for Cuenza on the left. So therefore, we can use them to test different scenarios of evaporate deposition and see if we can reproduce some of the observations that we have in these margins. And if you do so, we have tested many scenarios, but I only show one in that case. And we just start, you can see on the top right, we start from a low base level and we rise it at a constant rate. And if you do so, and you stopped after, in that case, so the timing is not really important because this can be changed. Just a rate which is based on some observation, but this could be scaled. But what is important that it stopped after 8 sorry. So it stopped after 800,000 years, and it reached the observations, the observed integrated evaporate volumes. On what we also see is that it also reproduces the thick distal evaporate that we observed in this system, but also the thin evaporate that we observed in the proximal. If we use the same rate in Cuenza, we actually also see that in 2 million years, we reach exactly the same elevation, minus 270 meters. And it also reproduces the integrated evaporate volume in this system. The only assumption here is that in this scenario is that the evaporates, they only form in shallow water lower than 100 meters. But with these scenarios, we can explain the base level evolution, and we can both explain the anti-correlation between evaporate volume and sediment thickness, and doesn't require any thermal anomaly to be explained. So to conclude, we have used, surface processes and related mass redistribution, including erosion, sediment transport, and deposition, are modeled using the extending stream polar law equation for fluvial processes. And we use diffusion equation for heat slope processes and marine deposition, which is, for the purpose of our research, a satisfying approach. I would say that in 3D, the diffusion equation, even so, you need to define different coefficients for basement on thing is, certainly must need to be improved. For example, if you want to model salt tectonics in 3D. But so far, these models, they provide a proper first order behavior of the mass redistribution related to fluvial erosion. So we have shown that surface processes, particularly erosion, sediment deposition, contribute to increase the normal fault offset on the formation of multiple synthetic fault, especially in the proximal domain. The erosional loading along transform margin can enhance the long-lasting flexural topography in the outer corners. In terms of base level, we know that a low base level is required for distal sediment bypass on wide-rifted margins. And the interaction between deposition and mid-crystal overflow mostly happen if these sediments can reach distal margin and then can form this tilted sedimentary succession on this sac basin. And finally, these thermomechanical models that couple with surface processes, they also allow for understanding the interaction between accommodation, subsidence history, and base level evolution. So thank you for listening.